Hello and welcome to the introduction to Chapter 7. Chapter 7 is on the periodic property of the elements. We'll see Chapter 7 has a lot to do with some of the nuclear trends on the periodic table. We'll start to think of many of these trends perhaps as we go from left to right across a row of the periodic table and then from top to bottom as we change within a group of a particular elements. So we'll talk a little bit about how the periodic table was devised. I think we know that it was devised by increasing, generally actually it was by the increasing mass of the element, but then also grouping the elements into similar sets of properties. The main property that's going to be responsible for the periodic behavior of the elements we're going to see is the effective nuclear charge. We're going to see that there's a size trend as we go from left to right and top to bottom across and down the periodic table. We're going to see that there's an ionization energy trend as well. We're going to see that there's a trend for how much energy it takes to remove an electron from an atom. That's the ionization energy. We'll see also there's a bit of a trend to the energy associated with absorbing an electron into the electron cloud of a particular element. And then we'll also discuss some properties of metals, nonmetals, metalloids to get some of the left versus middle versus right properties of the periodic table, and then also discuss some reaction trends as we get towards the end of the chapter. So let's first start by discussing the periodic table. It was put together by Dmitry Mendeleev. He's the one usually given the credit for assembling the periodic table. Lothar Meyer happened to independently, and very soon after Mendeleev published his work, he had come up with his assessment of these grouping of the elements as well. Now, what was being done is that the elements were being put in order of their increasing size, and from left to right, but then also by grouping the elements into vertical groups of similar properties. Now, this is the correctly assembled periodic table. Now, they did get a couple elements grouped into the wrong groups of the periodic table because they were particularly assembling the elements by increasing mass. It turns out that not every element increases in mass, that a few of the elements, as you go up in atomic number, there actually are some elements that have more protons in their nucleus but happen to weigh less. There's just a few examples of that, and they're not really worth pointing out. But one thing maybe worth thinking about is when some of these elements were discovered. Let's look at some of the first discovered elements. So like the ancient time elements are things like iron, copper, silver, gold, mercury, carbon, sulfur, tin, lead. These are some of the first discovered elements. Some of the later discovered elements are the ones like platinum, zinc, phosphorus, arsenic, antimony, bismuth. And then later came some of the elements like hydrogen and the other alkali, many of the other alkali metals, the alkaline metals, nitrogen, oxygen, fluorine. And so then one of the interesting sort of time periods is right up in between about, the mid to late 1800s is when you had the discovery of the electron. And so you sort of group the elements that we knew about before we discovered the electron, gallium, indium, germanium. These elements were also put into place. But then not until around the discovery of the electron do we discover the noble gases, the especially stable elements, and then as well some of the heavier lanthanide, actinide metals. And some elements are still being discovered today, primarily in this final row of the periodic table, because many of these elements, and actually those beyond uranium, in terms of atomic number, do not exist naturally. So a lot of these elements here have to be synthesized by colliding subatomic particles together to create usually a short-lived nucleus as a result. So the effective nuclear charge is that trend that's resetting every time we go from left to right across a row of the periodic table and then reset. So many properties depend on the attraction between the outer valence electron cloud and the nucleus. And so if we think about this particular picture, look at sodium. Sodium has 11 protons in its nucleus. Let me choose a different color. So if you look at the atomic number of sodium, of course you see that it's a 12 plus, or an 11 plus. It has an atomic number of 11, so it has 11 protons in its nucleus. And then it would have like a 1s shell, a 2s, a 2p shell of electrons spinning around the nucleus, and then that outer 3s orbital. So the outer one electron that's spinning in this s orbital here has an attraction for the nucleus that is sort of not experiencing that full positive charge in the nucleus of 11 plus. The inner core electrons are dampening or shielding a lot of that nuclear charge from the outer valence electron. Now, what we're going to see as we go from left to right across the periodic table, once you start looking at things like as you go across to, say, aluminum or into silicon, sulfur, that the outer electrons here are only really mostly being shielded by the core electrons. So the core electrons are going to act as a really good shields of this nuclear charge, but the valence electrons aren't really going to screen each other particularly effectively. So our Z effective is our usual sign for the effective nuclear charge being the symbol Z, that this trend here is going to be that it increases from left to right, and then it resets itself. So it starts relatively low, and then increases from left to right, and then once we get to a new group of elements, it resets itself. We're going to see from top to bottom that we get a small trend here that the effective nuclear charge is slightly increasing from top to bottom. So as we go from top to bottom down a group of elements, we'll see that there's a slight increase in the effective nuclear charge. Not a big increase from top to bottom, but we'll talk about that on the next slide. So this chart here is kind of showing us the sort of dependence of the nuclear charge on the effective nuclear charge. So if you look at the lithium, so like a 2s1, 2s2, 2p1. So like just sort of looking at the second row of the periodic table through neon and then restarting. The red curve is looking at the effective charge experienced by that inner 1s core electron. So the 1s electrons are effectively experiencing just about the entire full nuclear charge of the atom. So if you look all the way at argon, the Z of argon is 18. It's element number 18, so it's 18 protons in its nucleus. And so the inner 1s core electron of argon is experiencing just about that full positive charge of 18 plus. And if you look from the chart, you see a net increase as you go up in Z for the effective charge being experienced by that inner 2s, the inner 1s core orbital of these elements. But then if you look at the effective charge experienced by the outermost valence electrons, that's being described by these curves here. And one of the things that you can see is, just if you inspect the curve, is that they increase from left to right. That's why we're saying Z effective increases from left to right. And then it resets itself as you go to the next sort of row of the periodic table and you go down to sodium. Now, the blue and the yellow curve are being calculated using some advanced methods that aren't really worth talking about this particular point of this video. And the green's actually being calculated just by assuming that the core electrons are the shields here. So if you calculate or consider your effective charge is just your full nuclear charge minus S, one way of making an approximation here is that the effective charge is just equal to Z minus the number of core electrons, because the core electrons are acting as the shields here of that nuclear charge. And so this means that for lithium across to fluorine or to neon, that you're just going from a +1 to +8, because you're just simply subtracting the core 1s. So you're just subtracting 2 in the case of the second row of the periodic table. And then when you look at the sodium group for a 1s2, 2s2, 2p6, 3s1, you have these 10 core electrons being subtracted off here from the atomic numbers of 11 across to 18. So you're now resetting yourself to +1 to +8. So you get almost a resetting of your effective charge if the core electron count is exactly equal to the shielding effect. If you inspect the blue curve, you'll see that there is a slight increase from lithium to sodium, and for each element, if you go from top to bottom, you see that there is a slight increase as you go down a group. We can talk more about this as we go, but this is going to be related to the larger core electrons aren't shielding as good as the smaller core electrons. So if you start thinking of a relatively big element, like let's just think about potassium. So if we go down to the next element, that'd be element 19, so 19 plus, so it has 18 inner core electrons, that in order for the effective charge of potassium to be a little bit higher than that of sodium, what has to be the case is that these 18 core electrons aren't shielding as well as they were for sodium. So the core is growing in size, its ability to screen is becoming poorer. So the core electron screening ability is becoming poorer as those electrons become larger in size. Okay, so our general trends for effective nuclear charge increases across a period. That's where we're getting our big behavior of elements that are going to be easier to lose electrons on the left side versus elements that are going to be harder to take their electrons away on the right side, and then a resetting of this trend from top to bottom. So this is why we see like lithium, sodium, potassium that the alkali metals are all sharing this trend of forming the positively charged cations as a result of having this one extra valence electron, and then also a resetting of the effective charge that that electron experiences with its nucleus. And so then if we think about the size effect that the effective charge is going to have on atoms, if you just think, okay, as we go from left to right, what's happening is that the elements on the right side have a much higher effective charge. So they're experiencing a greater positive charge, and that's going to pull those electrons in more tightly. So even though you're just starting with one valence electron for lithium, going to two valence electrons for beryllium, 3, 4, 5, 6, 7, 8, etc. valence electrons, even though the valence count is going up from left to right, you see a decrease in size, but it's because of that increase in the effective charge that those electrons are experiencing. So they see a bigger positive charge that's going to take a lithium 1s from being a big atom to the fluorine being a 2p5 being a relatively smaller atom, because again, higher charge pulls those electrons in more tightly. And then we see an increase in size as you go from top to bottom. That's probably not too surprising, that if you go from, say, 1s1 to 1s2, 2s1 to 1s2, 2s2, 2p6, 3s1, that each time you add a new successive layer, you're increasing in size. So hydrogen smaller, lithium bigger, sodium even bigger. So we get an increase in size from top to bottom just simply because our outer valence shell is increasing in size. So the end value goes up from top to bottom, so the size increases. So decrease from left to right in atomic size, but an increase in atomic size from top to bottom. Now let's think about atomic size of uncharged atoms. The previous slide was considering all of those atoms being uncharged. So comparing sodium 0 to fluorine 0 in terms of their relative size, then what we could say is that sodium must be bigger than lithium, and lithium must be bigger than fluorine. Lithium and fluorine being in the same row relative to each other, and then we get a decrease in size across that particular group of elements. So we can say that sodium is definitely bigger than a fluorine atom. And if we flip back to the previous slide, or if you do, you can do it if you want, you can flip back and see that sodium indeed is a bigger atom than a fluorine atom. Now what if, though, we take away an electron from sodium and make sodium plus? So we go from having the neon followed by a 3s1 configuration to having just a neon configuration. I think it makes total sense that if we go from having 11 positive particles holding together 11 electrons where we have this big 3s orbital, and we lose the 3s electron, we're going to definitely decrease in size. So all cations are going to be smaller than their uncharged counterparts. So that's going to be a general case that we see each and every time. Even if you were to look at calcium plus, which isn't a stable ion, but calcium with a 1+ charge will definitely be smaller than calcium with a 0 charge. Because if we lose one electron, if you imagine going from an argon 4s1, comparing that to an argon 4s2, having that extra electron is definitely going to make the atom larger in the case of calcium 0 and then smaller in the case of calcium plus. So cations always smaller than their uncharged counterparts. If we lose another electron, then we can definitely say calcium 2 plus will be smaller than calcium plus. So this is going to be a golden rule that is always followed. The same thing happens if we add an electron. So if you go from having a 2s2, 2p5 to now adding an extra electron, 2s2, 2p6, you're adding one extra electron with the same nuclear charge to keep it all held together, then we definitely have to have an increase in size. So anions are always going to be bigger than their uncharged counterparts. So this is a general rule, or really a golden rule, that we're always going to see followed, that any substance or any atom with a negative charge is going to be bigger than its uncharged counterpart. If you look at O-, definitely going to be bigger than oxygen atom, and then O2- definitely even bigger as we keep and continue to add electrons. In terms of stable ions, we're going to stop obviously at the noble gas configuration is the most stable. We'll talk a little bit later about electron configurations of cations and anions though. For sodium plus versus NaF, let's think about this for a second. This is actually a sort of clever problem of comparing these two ions now, because they each have 10 electrons. So each ion, so if you notice, sodium has 11 electrons if it's uncharged, lose an electron now goes down to 10. Fluorine has 9 total electrons, add an extra one goes up to 10 as well. And so these electrons all have the neon configuration. So they all have that 1s2, 2s2, 2p6. So if you think of this configuration of electrons of having a 1s, a 2s, and the 2p set of orbitals, wouldn't it make sense that if these are negative particles spinning around these orbitals, that if you have a higher positive charge, then it's going to make those electrons be closer and more attracted to the nucleus and smaller as a result. So the issue here is that sodium plus ends up being smaller than F minus because they both have the exact same count of electrons, so they're isoelectronic is a fancy word for that. So these are isoelectronic with each other, the exact same electron configurations. And then sodium ends up being smaller because it has 11 positive particles to keep all those electrons together versus only 9 protons for the case of fluorine. So if you go back to the uncharged counterpart though, still sodium is bigger than fluorine because once you have the extra 3s, sodium's bigger than sodium plus, and then F is compared to F minus is smaller, so then F ends up being smaller than sodium when we apply our left to right uncharged or same charge rules for sodium versus fluorine. Now let's do one last example. This is a weird case. These aren't common ion. Well, for one of these, this is not a common ion. But if you're comparing the size of Na plus with F plus, whenever the charges are the same as each other, then you can just revert to the general atomic trend, that sodium is going to be bigger than lithium, which is going to be bigger than fluorine, like we established earlier. And then if you add a positive charge to each of these, and sodium plus is still going to be bigger than lithium plus, and lithium plus is still going to be bigger than fluorine plus. So whenever the charges on our ions are the same as each other, we use our left to right atomic trend for size. Whenever the charges are isoelectronic and the electron counts are isoelectronic, we have to apply the thought of comparing the number of protons in the nuclei of the atoms to keep them held together. So whenever we have isoelectronic atoms, we got to look to the nuclear charge to see and make our size trend. So the size of our ions, let's compare here where we have O2 minus. So O2 minus would have 10 electrons. Compare that with F minus, 10 electrons. Same for sodium plus, magnesium 2 plus, aluminum 3 plus. And notice the size trend here, that oxygen has the fewest protons in its nucleus, F more protons, sodium even more, same thing with magnesium and aluminum. So aluminum ends up being the smallest because it has the greatest charge to pull that same electron count in, so smaller, 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 just going with the trend of the proton count. So a greater proton count keeps the same number of electrons held in more closely together and makes a smaller ion. So ionization energy is the minimum energy required to remove an electron from the ground state of a gaseous atom or ion. This is just relatively important if we think of what the ionization energies mean. So like if we look up the IE of sodium, it's 495 kJs per mole, means that the sodium gas going to sodium plus, still a gas, plus an electron has a delta H associated with it of 495 plus 495 kJs per mole. So the delta H of the reaction would be plus 495 kJs for 1 mole of sodium turning into 1 mole of sodium ion plus electron being freed up. Now the key here is that this works for gaseous substances. This isn't going to be the exact same delta H if you had aqueous or solid substances. So this is specifically for gaseous atoms and ions here. And so the first ionization energy is the energy it takes to remove the first electron. You could establish the second ionization energy, the energy it takes to remove a second electron. You can imagine that removing a core electron off of sodium is going to take a lot of energy. So going from sodium plus gas to sodium 2 plus gas plus an electron is going to have a delta H that's going to be greater than 495 kJs, and by quite a bit since it's now removing a core electron. So let's compare some I1s versus I2s. So sodium, I guess it's 496, I said 495. But the second ionization energy, look, it's almost a factor of 10 higher because, again, removing an electron that's now much closer to the nucleus, so it's going to experience a stronger attraction. You could think about our energy of electrostatic attraction equation here. Remember this kappa, Q1, Q2, divide by D. So your core electrons are going to be closer to the nucleus, so they're going to take a greater amount of energy to remove, and they're also experiencing a greater effective charge. You might think one of these might be the charge of the electron, which is a constant. The electron just has its charge. The other Q2, you might think that might be related to the Z effective. So for sodium, removing one electron, you might think, okay, we have a relatively small effective charge and then a relatively large atom. In the case of sodium plus, we have a relatively now small atom with a relatively high effective charge. That's going to increase, and we see it increases the ionization energy by about a factor of 10. Now, magnesium is, of course, has a configuration of 2s2 on top of helium, or no, excuse me, it's a 3s. So it would be the configuration of neon followed by a 3s2. So removing the first s electron takes more than sodium. That might make sense because we're thinking as we go from left to right, as we go across the periodic table, our effective charge is increasing. And so as our effective charge increases, you also have a decrease in size. So the size is getting smaller. These are both in favor of an increase in the ionization energy from left to right. And so it probably makes sense that magnesium is going to have a higher I1 than sodium because it's experiencing a higher effective charge and has a smaller size. Both of those are going to be in favor of having a stronger attractive energy, so more energy to remove that electron. And then if you want to take away a second electron from magnesium, it's higher than the first. In fact, we're always going to see that that's the case, that the second is always going to be higher than the first. And then whenever we start removing a core electron, we're going to get a big jump. So if you notice for aluminum, we start at 578 for the first. We'll talk a little bit later about why that's not necessarily higher than magnesium, so it's a little bit nuanced. But then definitely higher for the I2, definitely higher for I3, and then very much higher for the I4, because that's when we start removing a core electron for aluminum. Silicon has 4 valence electrons, so you get the big jump for removing the 5th electron. And generally continuing this trend of increasing in ionization energy as we go from left to right. So our general ionization energy trend from left to right is that we're going to get an increase. We'll talk in a minute how there's a periodic inconsistency with this increase, but for a slightly nuanced reason that maybe we'll talk more about later. So this is our ionization energy trend from left to right increase because we get an increase in our effective charge, a decrease in our size. Both of those are in favor of having a more attracted electron to its nucleus, so more energy to remove the electron. And if you notice, we go up and then we actually go back down and then up, then down, then up. And this is mostly periodic, so we go up, down, or at least not up as high as you expect, up and down and then back up. So this is relatively periodic. I don't want to talk too much about the transition metals, but there's some interesting behavior where we get a general increase across the transition metal block with a little bit of noise. And then again, an increase, decrease, increase across the P block. Now, the nuance, I think it'll be better left with to talk about later, but it just has to do with the relative energy of an S shell electron versus a P shell, and whether or not we're removing from an orbital that has a spin-paired electron versus not having a spin-paired electron. But we'll talk more about that periodic inconsistency later. So we get an increase, generally, ionization energy from left to right due to the size and effective charge trends. But then if you look at the top to bottom trend, notice that mostly we're getting a decrease here. You get a few instances where there is actually an increase, so there's like a slight increase here, but mostly you get a decrease. You interestingly get an increase in some of these transition metals as well. But the main issue here is that as you go from top to bottom, the size increases. So the electrons are further away from the nucleus. That makes them easier to remove. So this is why the ionization energy trend tends to decrease as you go from top to bottom. It's because the size of the atoms are getting bigger, the valence electron's further away, easier to remove. So it just comes back to the Q1, Q2. Divide by D. If you have a bigger distance of separation of your two particles, then the energy of attraction is going to be less. So the energy of electrostatic attraction is lower if you have particles further away from each other. But we do get a small increase in effective charge with the same trend. So the effective charge does go up a little bit from top to bottom, and that's where we're getting some of this inverted behavior. And some of the instances where you see an increase from top to bottom, it's where you just happen to get a bigger increase in effective charge than the size increase from top to bottom. So not super important to memorize or to know specifically where you see some increases from top to bottom, but just like generally you get a decrease in ionization energy due to the increasing in size, but then occasionally you see an increase in ionization energy from top to bottom, and you can explain that just through how the effective charge does somewhat increase from top to bottom. So let's look at the electron configurations we expect to find for ions. For cations, the electrons are actually lost from the largest orbitals first. Those are going to be the orbitals that have the greatest N value that happen to also have the largest possible L value. So let's look at a couple of examples. So for calcium, think first of calcium with no charge. That's going to be the easiest way to make sure we get a cation configuration correctly. So think calcium 0 first. Argon followed by a 4s2. Now, this atom's actually pretty easy to come up with the 2+ ion, because we're just going to lose this largest 4s orbital and the 2 electrons from it and just come up with the argon configuration. So calcium 2+ is just simply the argon configuration. Okay, now if we picture iron with a 0 charge, that would be argon followed by a 4s2 3d6. Look at a periodic table if you're not sure, but you'd see iron is a 3d6 in terms of an uncharged atom and its expected configuration. Now think of these orbitals, which one's larger? Because the larger orbital is going to be the one further away from the nucleus, and it turns out those electrons are going to be easier to ionize. And so in the case of iron, that's going to be the 4s subshell electrons are going to be the larger orbital. This goes back to our picture for filling in our orbitals. If you remember when we did this, we're thinking 1s, 2s, 2p, 3s, 3p, 4s, and then the 3d was filling back into the n equals 3 space. We were pointing that out primarily so you can see that this n equals 4 orbital is definitely bigger than the n equals 3 3d subshell. So the 4s further away from the nucleus, easier to ionize the electron spinning around that orbital first. So iron 2+ is going to lose the 4s2 electrons. So iron 2+. Now this is what we expect. This is not the anomaly. This isn't some weird case. This is what we expect to find every time for an atom like iron, is its configuration would be 3d6. So iron 2+, 3d6. Then if we need to lose a third electron off of iron, then we go to the next biggest subshell. So we look for the greatest n value orbital with the greatest L. So iron has 3s, 3p, and 3d electrons, so it's going to lose one of the d electrons first because it has the highest L of those same orbitals of the highest n value of 3. So we're going to now go to argon 3d5. Now it would be kind of weird to start losing a core electron in favor of what we've already termed valence electrons as well. So you can imagine, it seems as if taking away these electrons first makes the most sense. And we're just simply going to remove them in order of the largest electrons first, then the next largest electrons next. You can also piece together a valence orbital diagram, so you might picture the 5 3d orbitals. So we know there's 5 3d orbitals, so we should get 5 spin paired electrons. So iron 3+ we would predict should have 5 unpaired electrons. And then iron 2+, like iron, should have just 4 unpaired electrons if you fill those diagrams in. So you can come up with electron unpaired counts. Those are just making sure we're picturing the correct configurations. Now, anions aren't particularly tricky. They're just filling in electrons in order of the orbitals from which we already filled them in. So if you look at oxygen without the charge would be a 1s2, 2s2, 2p4. We're just filling in the extra 2 electrons into the 2p subshell. So nothing really complicated for O2-, just a 1s2, 2s2, and a 2p6. And of course that's a neon configuration, which is good for that ion being a stable ion in perhaps solution. And 3- n is just a 1s2, 2s2, 2p3. So that's, of course, just ends up being the neon configuration as well. And then lastly, for argon with a minus, you just fill into the next higher energy orbital. And so the next energy orbital for argon, argon being a neon, so argon with the 0 charge would be neon, 3s2, 3p6. So this will just simply be the argon shell followed by a 4s1. Now, you would probably expect argon minus. This isn't going to be a stable ion because this is a high energy orbital. It's going to take a lot of energy to put that electron in that high energy orbital. So we're probably going to expect that that won't be a stable ion that exists naturally. So let's look at the trends for adding an electron. So the electron affinity is the energy associated with absorbing an electron in. So if we look at F, for example, if we take the F fluorine as a gas, so F gas plus an electron going to F minus as a gas, that the delta H of that reaction would be minus 328 kJs per mole. So this chart is looking at these values in kJs per mole of the element. And so this delta H of this reaction would just be minus 328 kJs. We can get that from the electron affinity of fluorine. So if you notice, as you go from left to right, there's this general trend that we're becoming more negative as you get towards the left. Now this probably makes sense because as we go across the periodic table, our effective charge is becoming higher. And so the new electron should be more attracted into that more highly charged nucleus. Now the noble gases are especially high because there's nowhere for that electron to go other than a higher energy subshell. So the noble gas groups are all highly positive, so we're not going to find the negative ions of the noble gases as stable existing ions. And also notice that the nitrogen group is particularly maybe not as negative as some of the other groups, or in the case of nitrogen, even positive. And this is because you're spin pairing these electrons. You're going from having nitrogen as like a 2p3 configuration and then spin pairing and creating that repulsive energy of now having an extra electron spin paired with another. And the same thing happens in the 2a subshell well, it's slightly different here where we take beryllium, ends up being positive because we're putting the extra electron from a 2s into a higher energy 2p subshell. So it takes more energy to put that electron into a higher energy subshell. So electron affinity generally becomes more negative from left to right towards the halogen, stopping with the noble gases, and the exceptions are the noble gases because the energy it takes to put an electron into a noble gas is a lot higher because of the higher energy subshell that we have to put the electron into, and then spin pairing for the 5a, the nitrogen group, and then the higher energy 2p subshell takes more energy for the group of 2a elements. Now there's not much of a top to bottom trend with the electron affinity. In fact, you can see that there's some chaotic behavior, so there's not much of a top to bottom trend here for this particular trend. So this chart here is looking at the metallic character of elements. So we actually have an increase in metallic character towards the bottom of the chart and then towards the left side of the chart. So we get more metallic character towards cesium and francium on that side of the periodic table. And then that makes sense. Just think of where do you not find the metal? Be helium. So you're going to increase the metallic character away from helium and then down from helium. Okay, and so we'll see a few trends are tied to this, such as the behavior of oxides. We're going to see that the metal oxides are going to increase in their basicity from left to right. So the more metallic the metal, the more basic the oxide. Then we're going to see then the more acidic the oxide, the more you're on the non-metal side. So the less metallic makes for acidic non-metal oxides. We'll talk about that trend later in class though. So there's a little bit of trends involving the metals versus non-metals in terms of some of their reactive trends. We also get the metalloids in the middle. I wouldn't necessarily bother memorizing the specific metalloids, but those are the elements that have sort of a blend between being a metal versus a non-metal. One of the things you can think is that most non-metals have relatively low melting points and boiling points, and metals have relatively high melting points and boiling points. You tend to think of these as being malleable and ductile. You can pound them into sheets, stretch them into wires. But the metalloids end up having relatively high melting points and boiling points, but then they're more brittle. So you can't really pound them into sheets or make wires out of them. But it turns out you can make semiconductors out of many of these elements, and they have some interesting properties. Okay, so our final slide for this particular presentation is on metals and how they differ from nonmetals in terms of the ions that they form. Of course, we know our nonmetals are forming minus charged ions when they pair up with other nonmetals. Hydrogen can form this weird hydride ion when it pairs up with other metals like calcium hydride, but it's not going to form the negative charge state with other non-metallic elements. But we see N3 minus, P3 minus, O2 minus, that the number of electrons it takes is just the electrons it takes to get over to the noble gas configuration. And so then on the left side, our metals are forming only positively charged states. So the metals all form plus charged states, no minus charged states on the metal side. And we're also generally not forming ions with our metalloid elements either, and some of the elements in between. And so some of these ions, you can see some of the common ions, like for vanadium, 5 plus and 4 plus, chromium just a 3 plus. We don't expect you to memorize these particular charges, but you can just gain an appreciation for some of the commonly formed charge states of some of these metals from a chart like this one. But again, only +1 for alkalis, only +2 for the alkaline group. Hydrogen's weird here, it's not a metal, but it does form, of course, the H plus ion in solution. And also you can describe, that oxidation number +1 when hydrogen pairs up with the non-metallic elements. Okay, so that's all for this video. We'll talk more in class as we go throughout the class about some of the periodic reaction trends for some of the different groups of the periodic table. as we get towards the end of Chapter 7. All right, thank you for the attention.